Hello geometry students, my name is Jami Amy and this is the first video discussing our course together. Before you watch this video, I want you to do one of three things. One being print the presentation with blanks. Option 2, if you don't have a printer, download the presentation onto a tablet that you can write on and fill in the blanks that way. And option 3 is if you don't have a tablet you can write on and you don't have a printer, then still download the presentation with blanks and then have a piece of scratch paper and you can write what goes in the blanks on that piece of scratch paper. So please pause this video and make sure you have done one of those three things before continuing. Welcome back, and this video is our discussion on Chapter 1, A Beginning of Geometry. Nice picture there of Euclid. He's the father of geometry, born in 300 BC. And the word geometry comes from the Greek language that means to measure the earth. This textbook, all of our videos are aligned with this textbook here. You're welcome to buy a copy of it if you want. You do get an electronic copy of it with your My Lab and Mastering access code. Okay, so section 1.1 is on tips for success in mathematics, and I'm going to skip that. So this video is going to discuss section 1.2, geometry as a mathematical system, and 1.3, points, lines, and planes. Okay. Figure assumptions. We may see geometric figures, and at times we can make assumptions about the figures, and at times we cannot make assumptions about the figures. It's important to know what you can assume and what you cannot. So the first picture is right here, and my question is for you is, can you assume that that is a line? And the answer is yes. If you see a figure like this here, my question for you is, can you assume that that is a right angle? The answer is no. Look at the third figure though. Can you assume that that is a right angle? And for that one, the answer is yes. So notice the two arrows that make the line. Notice the two arrows that make up the right angle, but more importantly is this symbol right there. That is geometric code for 90-degree angle or right angle. Okay, if you have two segments that look like this, my question is, can you assume that the segments have equal length? The answer is no. Next figure though, can you assume that these two segments have equal length? For that, the answer is yes. I want to show you one more geometric code that will allow you to assume two figures have the same length. If you have two segments like that, and you see two tick marks like that, for geometric code, that means that those two segments are congruent, or they have equal length. Now, if that single tick mark is already used up in your picture, you can step it up to a double tick mark. If they both have it, it means that they are congruent or have equal length. All right, next figure, you see this one here. Can you assume that that is a square? The answer is no, but look at the one next to it. Can you assume that that is a square? And the answer to that is yes, and that is because our geometric code tells us by these little corners that we have all 90-degree angles, and by these tick marks that all four sides are congruent, and that covers our definition of a square. All right, so figure assumption, and you'll learn more as you go. You know what, I want to show you one more before we go on. If I draw two angles, let's say it's an acute angle like that and acute angle like that. Notice I didn't measure them, I just sketched them. At this moment, you couldn't assume, anything about their measures, but I put an arch mark like that and a matching single arch mark like that. Now you know that that is geometric code, that those angles are congruent or have the same measure. All right. There are some undefined terms in geometry. They are the most basic term that we do not formally define. but have a meaning or description that we've at least agreed upon. So the first term being point. A point has no dimension, no length, no width, no height. It does not have a location. It does have a location, however, or a position. For example, you've seen points that have location notated like this here in the rectangular coordinate system. To name a point, you can use a single capital letter. For example, you can write point A like that, or you can put that single capital letter above a point like that there. Both of those would be read point A. Line is the next term. That's undefined. A line extends in opposite directions without end and has one dimension, and that dimension is length. A line can be named by using a single lowercase letter, like this here, line, and then lowercase l. You can see it right here on the figure, or by any 2 points on the line. So that could be AB, and you would put this arrow over top, this symbol over top with 2 arrows, or you could write BA with that same symbol over top that has 2 arrows. All 3 of these, 1, 2, 3, are ways to identify or name this line right here. Our next undefined term is a plane. A plane extends in 2 dimensions without end. The 2 dimensions are length and width, but a plane does not have thickness. Name a plane by a single capital letter or by any 3 points on the plane, non-collinear. That means 3 points that are not in a line. So for example, you can name this plane right here. You can just put a capital P on the outside and then you can call it plane P. That's a way to name or identify it. Or you can name it plane ABC, where A, B, and C are all points on the plane, but notice that all 3 points are not in the same line. Okay? All right, so let's practice naming points, lines, and planes. First off, let's write 2 other ways to name the line QT. Okay, I'm first gonna highlight, no, I'll circle it. I'll circle the line QT. This figure here, picture holding a book. And you're holding a book, and then you take a pencil or a line, and you shove the pencil through the middle of the book. So the top of the pencil sticking out here, and the other half of the pencil is below the book. It went through it. So this figure is representing something similar to that. Erase my scratch work. And one way you can tell is by these dashed marks here. Whenever you see a dashed line like that, it means that if you were actually holding this figure in your hands, if you were looking at it in 3-dimensional space versus the 2-dimensional space on our computer screens, you wouldn't actually see that part of the line. But it still exists, so we used a dashed line to represent it. So back to part A. Write 2 other ways to name that line QT. Okay, well, I can name that line lowercase m. Let me spell it right first. Line lowercase m, by that lowercase m right there. That's one way to name a line. And a second way we could name that line is any 2 points on it. Well, I don't know any 2 other points, but I can go with the T, then the Q. Doesn't matter which order. That is just a different way to name that same line. B. Write 2 other ways to name plane P. Okay, plane P can also be named by listing 3 points on the plane that are not in the same line. So you could go with plane and then list 3 points like R, V, S. Or you can go with plane, I'm going to use 3 different points this time, Q, V, S. Caution using plane RQS. The problem with plane RQS is that R, Q, and S are all on the same line, which means that this right here would not identify this one unique plane. There are other planes that exist that pass through R, Q, and S, so that would leave room for interpretation which plane you're trying to identify, and therefore we cannot use R, Q, and S. Okay, name 3 points that are collinear. Well, we just did. R, Q, and S are all on the same line. I'm going to put those points above to clarify that they are points. Name 4 points that are coplanar, and that means on the same plane. So 4 points, I'm going to separate these with commas there. 4 points on our plane would be V, R, Q, and S is also on our plane. Careful, lowercase l is not a point on the plane. That's a way to name this line right here. And capital P is not a point on the plane. And you can tell because it does not have the dot next to it. All right, last one. Name 3 points that are not collinear. So 3 points that are not on the same line. So T, that's kind of a point above our plane that we haven't talked about in a while. V, that's definitely on the plane there, and we'll throw in R. That would be 3 points that are not collinear. There are other options too, like TQS, SRV, TQV, lots of different options. Just name their 3 points, separate them with commas, put dots above, and make sure that one single line cannot pass through all 3 of those points, and you will have a correct answer of 3 points that are not collinear. Okay, I'm going to erase my scratch work now, and I'm going to put the answers up, typed up, so that if you couldn't quite read anything that I wrote with my finger, then you can at least see it here. You can also see different variations, like on C, D, and E. I wrote the word points instead of putting the dots above, stuff like that. All right, more undefined terms. Our next undefined term is a line segment. It is part of a line. It consists of 2 endpoints and all the points between them. To name a segment, you would want to name both of its endpoints. So not just any 2 points on the segment, you've got to name the 2 endpoints to identify a unique segment. So in this case, you can name this as AB with the line over top. And when I say line, I don't mean line as in the undefined term line, because there are no arrows. See, these arrows are not there. If these arrows were there, then you would be naming lines. So I'm going to erase them. So you could name this segment as AB with that segment over top, or BA with that segment over top. It doesn't matter which order you put the endpoints in. You'll often see them in alphabetical order, but it's not inaccurate to write BA. The next undefined term is array. Array is part of a line. It consists of endpoints. It consists of just one endpoint and all of the points of a line on the other side of that endpoint. You name a ray by its endpoint and any other point on the ray. Now this time, the order of points does matter. So for example, look at this picture here. If you were trying to somehow name that ray, identify that ray, write down that ray is your answer, you would want to put the letter B first, because B is the endpoint, then any other point on the ray, and we only know one other point on there, so that's A. And then make sure your ray over top, the arrow is above the A. Let's look at this one here. This ray is different than the other one. It has an endpoint of A, and then it passes through B. So be careful to make sure the symbol above represents that as well. Opposite rays share the same endpoint, and they form a line. So name each opposite ray as you would name a normal ray. Okay, so look at this figure here. There is a set of opposite rays here. They have the same endpoint, which is C, and the first ray, I'll go with this way because that's what's listed first. Passes through B. And then the opposite ray of that also starts at C, but it goes in the other direction, passing through A. And notice that the combination of those two opposite rays does form a line. All right, I would like you to pause this video now and try these 3 parts to this example. Welcome back. Grade your own work. Let's see how you did. If you put DE or ED and EF or FE, and last DF or FD, then you named all 3 segments in the figure. They are here, here, and all the way D to F. So those are the 3 segments that I've highlighted in red, 1, 2, and 3. And there are 2 ways to name each because the order of the endpoints doesn't matter. Part B, if you put ED, EF, DE, or DF, that's the same ray. I'll show it with some colors in a moment. And FD or FE, then you got all of the rays. Let me show you with the different colors. Okay, erase that. Let's get a blue. Okay, the first ray, ED, is right here. E passing through D. The second ray, EF, is right here. E passing through F. And those are actually opposite rays too. The third ray can be written as either DE or DF. It starts right here at D, and then it travels this way forever, which passes through E and it passes through F, which is why you could name it DE or DF. And the last ray in that figure, there's 4, can be named as FD or as FE, and that's because it starts right here at F and it heads this direction forever. And that would pass through E and it passes through D, so you can name it as FD or FE. Either one works. So 4 different rays in that figure. All right, last one. Which of the rays in part B are opposite rays? Oh, we talked about that already. It's these 2 just briefly. The opposite rays are ED and EF. One way to know that they're opposite rays is to look at the endpoints. They have to be the same, E and E. So check that off. And then just check in the figure that D and F had those rays in opposite directions, making opposite rays. Okay, theorems are statements that we prove using logic and other previously proved theorems. Postulates are a little different than theorems. Postulates or axioms are derived from theorems and therefore not proven independently. We're going to be using different theorems, different postulates or axioms in our proofs. So as we list the different postulates and theorems, maybe find one common place that you can write them all down for quick reference, or if you're good about referring back to your notes, that will help as well. Okay, postulate, the first one we're looking at here is 2 points determine a line. That postulate says that through any 2 points there is exactly 1 line. Line T, right here, passes through points A and B. Line T is the only line that exists that passes through both those points. And that's kind of hard to believe, but try to draw any other line and have it pass through A and B. It's impossible to do. Only 1 line exists passing through any 2 points. So the postulate is 2 points determine a unique line. Let's head this way. Intersection of lines. If 2 distinct lines intersect, then they intersect at exactly 1 point. It's hard to believe that you can draw 2 lines and they can only intersect at 1 point. Now this is if they're not the same line, of course, but I'll get into that. But it is true. Try to draw any 2 lines that aren't the same line, and they will intersect at 1 and only 1 unique point. And that would be, for this example, the point C. Intersection of planes, however, if you have two distinct planes, that means they're not the same plane, they're not like sitting right on top of each other, then they intersect in exactly one line. And the line you can see here, it's ST for this figure. So the intersection of two distinct planes is a line, whereas the intersection of two distinct lines is a point. And if you're ever questioning this, if I'm talking about two lines, just pick up two straight edges. It can just be two pens or two pencils and have them intersect, and you'll see that they can intersect at one point. If I'm ever talking about two planes and you want to recreate that, just pick up two pieces of paper at your house, and you'll see that if you put those two pieces of paper intersecting, one here and one, well, you wouldn't have it passing through the other paper, it'd probably just be sitting above, but you'll see that those two pieces of paper are touching at one distinct line. All right, last postulate on this slide is 3 non-collinear points determine a plane. Through any 3 non-collinear points, there is exactly one plane. So for this figure here, points Q, R, and S are non-collinear. So plane P is the only plane that contains them. I said it before, but I just want to point out again, capital P, it can really look like it's a point on the plane, but it's not. If it doesn't have the dot by it, then it is just a name. It's like a label on your shirt, okay? It's like, okay, that right there is plane P, okay? All right, finding the intersection of two planes. So look at each surface of this box shown. Each of the surfaces represent a part of a plane, like a piece of paper, for example, a shoebox. What is the intersection of plane ADC and plane BFG? Whoops. Okay, so let me highlight those two planes with a color. First one is plane ADC. So ADC, the only plane that exists through those 3 points is this one here. Okay, let me change colors. The next plane is BFG, B to F to G. The only plane that exists passing through containing those 3 points is this one here. So what we are asked to determine is the intersection of those 2 planes. Where do the blue and the red shading meet? Okay, and we know that two distinct planes always intersect at a line, and this is supporting that right there. They're intersecting at that line BC, or the segment rather, BC, that is a part of the line BC. So the answer would be the planes would intersect at line BC. And that's because we're having those planes extend indefinitely at in all directions, even though this picture here is just showing a part of each of those planes. All right, that will conclude our discussion on sections 1.2 and 1.3. My name is Jami Emigh. Thank you for joining me, and I will see you next time for our discussion on section 1.4.